Sometimes a micro-ohmmeter able to measure very low resistances, as low as 1 micro-ohm, is quite a useful tool. For example, when measuring contact resistance of relays, switches, fuses, other mechanical connections and contacts. It can be used to test transformers, rotors of electric engines, and so on. And in electronics troubleshooting, it also can be used to inject a constant current into a shorted circuit to help locating the shorted component. 1 to 2 amps is quite a bit of current, usually enough for the shorted component to heat up. But commercially available meters could be quite expensive, and the cheaper ones may lack the resolution. Also, cheaper ones may use only 100 milliamps of current or so maximum, and this might not be enough for some applications. But an excellent micro-ohmmeter design based on the Arduino Nano controller was published in the Server magazine some time ago, and it is able to measure the resistance in 1 micro-ohm resolution. I'm not the inventor of this design. All the credit and thanks for this circuit go to the original designer, Dennis Walrath. Given its low price, I just decided to build it for myself, and then implemented some improvements to make it a little more versatile and functional. The links to both the original version published in the Servo magazine and my adapted version are provided under the video. Okay, so now I will go through the changes that I made to the original schematic and also the Arduino code. First, the original version uses 3 lines of the OLED display to indicate resistance in micro-ohm, see micro-ohm, milli-ohm, and ohm resolution. In practice, I find such triple way of showing the resistance a little too difficult to read, at least for my taste. Therefore, I just left the resistance value in ohms to the 6th decimal point, that is to 1 micro-ohm resolution. I feel this is cleaner and simpler. Second, with the original version of the code uploaded, the screen flashes each time the value is updated, that is every second, and this is quite annoying. Therefore, I changed the code so that only the digits renew, and the screen does not black out, it doesn't become black and flash again. Third, more calculations are added in my code. The code is programmed to show not only the voltage of the battery, which is marked B, battery, but also the current that runs through the test resistor. I is current, you see, 1.35 amps currently. The battery voltage and the current through the test resistor are rounded to 2 decimal points. Also, I included the indication of the voltage drop on the test resistor. Now there is 0 because I just connected the probes together. And the power dissipated, also 0 currently, power dissipated in watts. These two values are rounded to the 4th decimal point, that is 0.1 millivolt and 0.1 milliwatt resolution. Voltage drop is useful in finding shorts, for example. If there is a shorted component, such as a capacitor, in an array of similar components, the shorted one will have the lowest voltage drop on it, making it easily detectable. Fourth, I decided to implement an option for averaging of 10 last measured values. For that, a toggle button was mounted. When it is pressed, the digital pin 2 of the Arduino is pulled to ground, and the program displays the average value of 10 last measurements. Let's see? Yep, see? Average value. The code also accounts for debouncing, ensuring that the button does not trigger multiple times due to mechanical bouncing. Therefore, you need to keep the button pressed until the function on the OLED screen changes. let's say we go back, measured value, see? And then we press it again, average value, measured value. Keep in mind that the original code incorrectly names the sense resistor as 5 ohm resistor, probably because this was the initial setup, which was later changed and improved by Dennis. I renamed it in my code, even though this has nothing to do with the operation of the micro-ohmmeter. Fifth improvement implements a few changes in the schematic of the device. My version uses 3 15 ohm 10 watt resistors in parallel for setting the current. You can see 3 15 ohm 10 watt 1% resistors. They heat up during the high amp operation, so I mounted them on a heatsink. Also, I implemented an option to connect another 15 ohm 10 watt resistor in series with the 3 for a lower current measurement. See, 15 ohms resistor, the same kind of resistor. And I can switch to low amps measurement. And you see 0.37 amps, which is 370 milliamps. Back to 1.36 amps. Sometimes current of more than 1 amp is too much to handle for the device under test. So now the measuring current can be switched from approximately 1.2 amps to 300 milliamps. That depends on the load also. Keep in mind that 300 milliamps will not be enough for a true 1 micro-ohm resolution measurement. This has to be taken into account. Sixth, I included in my version a circuit to charge the batteries from a 5-volt charger. I implemented two 18650 lithium-ion batteries in series to supply voltage above 6 volts. But when the toggle switch is set to the charge mode, I put it to the charge mode, batteries are disconnected from each other and both are charged with 2 separate charging circuits. 2 separate charging circuits here. This way there is no need to have a balancing circuit to equalize the charge. The charging is configured to provide a slow charge, so it will take quite a few hours to charge the 18650 batteries. Smaller batteries, I don't advise using smaller batteries as they may not be able to handle the current of above 1 amp. For switching, a double pole, double throw switch is used here. See, this is neutral, it's just disconnected. I switch it on, and if I go to the other side, it's to charge, and there's a charge port on the side of it to charge the batteries. In my version, I also used a 10 microfarad tantalum capacitor for the voltage supply pin of the ADC converter, soldering it as close to the pin as possible to reduce noise. The 100 nanofarad capacitor marked C1, here it is in the schematic, is also moved close to the supply pin of the IDC converter. It will help to reduce high frequency noises. Also, my unit has a USB port for updating the code on the side, and also a power supply socket. In case an external supply is opted, and it can be 5 to 10 volts maximum. When external supply is plugged, the batteries are disconnected. By using an external 10 volt supply, the current of almost 2 amps can be achieved, and such higher current may be useful in detecting a short in a circuit. But do not use voltages higher than 10 volts. Even though Arduino Nano is rated up to 12 volt supply, the voltage approaches the maximum which can be dissipated by current setting resistors, unless your resistors are very heavy duty. The micro-ohmmeter can be calibrated by measuring a precision resistor and changing this multiplier in the code to account for the differences in your device specifically. Also, the indication of battery voltage can be calibrated by changing this multiplier here, voltage calibration. But keep in mind that the battery voltage is not used by the Arduino Nano in any of the calculations. It only helps the user to see the charge state of the batteries. With these improvements, I find this is a very useful piece of equipment for certain applications. Let me demonstrate to you how it works. So I will connect the probes together, the Kelvin probes together. Wrong way. Even that has an impact on the resistance. Yeah, so you see, zero value, 0 micro-ohm. Okay, and then we connect this 100 milli-ohm resistor, and you can see now it's moving a little bit. It takes time to settle, and also the average value can be looked at. And if I move the probe to here, you see how sensitive it is. It takes the resistance of the lead into account also. So now I move it here, maybe it's even more, 1 more milliamp or so. So another resistor, that's a 10 milli-ohm resistor. You can see now it says 9.8 milli-ohm. Yeah. So the original article by Dennis Walrath, published in the Server magazine, explains the principles of operation and components used. If you decide to assemble this micro-ohmmeter, take care to follow Dennis's directions and use proper precision resistors, especially the 5 ohm one, or 15 ohm in my version, and the 0.1 ohm sense resistor. I suggest toggle switches rated to at about 5 amps. Using the attachments under the video, you can download the zip file containing my version of the device, including the schematic itself, the sketch, and the necessary libraries. And when uploading the sketch to the Arduino, choose the old bootloader. Hope you found this video and the project educating and useful. Thanks for watching.